Welcome to another awesome edition of Comet Algebra. This video is for Algebra 2, Chapter 6, Section 8, Graphing Polynomial Functions. And this is probably one of the easier sections in the chapter, so it's a nice way to end it. Now, in a typical polynomial function, we knew this already, that the number of answers, the number of zeros, the number of roots, these all mean the same thing, is equal to its degree. And we're going to look at some pictures now, some graphs of polynomials in different degrees. So the first example is a constant function where the degree is 0, n is 0. So I just picked an example where the polynomial y equals 4. So when we're graphing this, we would come up here to, and now let's see if I can make a straight line. Okay, not horrible. So this straight line, this is a graph of a constant function. Next, we're going to look at a linear function where it is a first degree. I picked the linear function x plus 2 for our example, and I attempted to draw a straight line. Sorry, it's the best I could do. And of course, that's what a linear function looks like. So a quadratic function, we know that's a second degree when n is equal to 2. So the quadratic I'm going to choose here is just x squared minus 2, which we know is the same shaped as the parent equation, but it's just been moved down 2 units. So if I try to graph this accurately, it would look something like this. And that's the graph of a quadratic. A cubic function is when the n equals 3, or we have a third degree, and the one that I'm going to choose to graph is x to the third minus 4x. Okay, not perfect, but that's what a cubic graph looks like. It has 2 turnarounds. Now in a quartic function, when the degree is 4, it's a fourth degree, the fourth degree that I picked to look at is x to the fourth minus 5x squared plus 4. So I'll try my best to graph this accurately. Okay, not too fabulous with this pen, but you can see that a fourth degree, this one is in the shape of a W, and if we have a negative sign in front, it would be upside down, which would be the shape of an M. Okay, a quintic or a fifth degree equation when n is 5, we'll look at that graph. The fifth degree that I chose to graph is x to the fifth minus 5x to the third plus 4x. So I'll give this graph a try. You should graph that on your calc just to look at it, because my drawings are pretty poor with this pen. But anyway, you can see what these graphs look like. And now in class what we're going to do, we're going to look at these, but we're going to put a negative sign in front of the highest exponent, the highest term with the exponent, to discover something about end behavior. But in the video here, we'll just talk about it. The definition of end behavior is just what the graph is doing on both ends, to the left as it approaches negative infinity, and to the right as it approaches positive infinity. So if we just look back up here at the end behavior of some of these, our quadratic graph, the end behavior would be, we would just say up, up. Our cubic graph here would be down, up. The quartic one that we chose is up, up, and the quintic is down, up. So you're just describing where it's going as it goes off in both directions. So if you look carefully at the end behavior of, first of all, even degree equations, like second, fourth, sixth, and so on, and you look at what happens when you have a positive leading coefficient versus a negative, you'll see a pattern develop. In an even degree with a positive leading coefficient, the end behavior is always up, up. And when you have an even degree and the leading coefficient is negative, the end behavior is always down, down. And if you looked carefully with odd degree polynomials, you will see that if there's a positive leading coefficient, the end behavior is always down, up. And with a negative leading coefficient, it's always up, down. And there is going to be an easy way for you to remember this. Note that the leading coefficient tells you the end behavior to the right. And if you remember that in odd degrees, they're different, it's either up, down, or down, up. And in even degrees, the end behavior is always the same. They're either both going up or both going down. So if we know that the leading coefficient tells us the end behavior to the right, we can figure out the other one. So once again, if the leading coefficient is positive, the right end behavior is up. If the leading coefficient is negative, the right end behavior is down. And then, like I said, if you have an even degree, the end behavior is the same. If you have an odd degree, it's always different. One is going up, one is going down. And because of that, in odd degree equations, because their end behavior is one up and one down, they must have at least one real root, meaning where it crosses the x-axis. It's always going to cross once, so that's kind of a benefit for us. We always know we can find a real root because of their end behavior. There is always at least one x-intercept, which gives us that real root. Next word to define is extrema, and it just means it's the plural for one extreme, two extrema. It just means turning points. Your calculator refers to these as mins or maxes, and now you can see that sometimes a graph can have more than one max, and that's why you have to do left bound and right bound in the calculators to tell it which one you want. And note, there's a connection between the degree of the polynomial and what we call turning points. So if you just picture an x squared graph, it's a parabola. It has one turning point. It turns around once. Well, 1 plus 1 is 2, and that's the degree. A third degree equation is always kind of this S-shaped. It turns around twice. So it has two turnarounds, okay, plus 1 is the third degree. A fourth degree equation, like we found, it's either going to look like sort of the letter W, that would be a positive leading coefficient, or it could look like an M is a negative leading coefficient, but either way, there's three turnarounds. 3 plus 1 is the degree of 4. And then a fifth degree, if we want to look at that, could be a graph like this. It has 4 turnarounds plus 1, a fifth degree, and this goes on and so on. So please note the degree is one more than the number of turnarounds on the graph. So just by looking at a graph, you can tell what degree equation made it. All right, last thing we're going to look at. Just by inspecting the graph, you should be able to determine two things: the number of real zeros that the graph has and its degree. We can also tell if the leading coefficient is positive or negative just by looking at the end behavior. So let's look at this first graph. We'll call this graph number 1. How many real zeros does it have? Well, you can tell the real zeros by how many times it crosses the x. So we're looking for x-intercepts. So this has 1, 2, 3. This has 3 real roots. And now we need to determine the degree. So look at how many turnarounds there are. There's 1, 2 turnarounds. Therefore, this is a third degree equation. And remember, we can look at the end behavior to the right to determine if the leading coefficient is positive or negative. Well, this graph number 1, to the right, it's going up in the positive direction. Therefore, this has a positive leading coefficient. Let's look at graph number 2 here now. Again, how many real zeros does it have? Well, it only crosses the x-axis once, so it has 1 real. Now, in your assignment, they're going to say, well, then how many imaginaries does it have? Well, before I can answer that, let's look at the degree. It has 2 turnarounds, therefore this is a third degree equation. So now that I know there's 3 answers, One of them is real, therefore 2 are imaginary. And this off to the right is going down in the negative direction, so this has a negative leading coefficient. Graph number 3, same questions. The number of real zeros. This one does not cross the x at all, so this has no real solutions. Before we answer how many imaginary there are, let's look at the degree. There's 3 turnarounds. This is a 4th degree. Therefore, we know there's 4 answers, and all of them must be imaginary because there's no real ones. The end behavior to the right is in the negative direction. Therefore, this has a negative leading coefficient. Oh, I can't even tell those are F's. I'll try again here. All right, the last 2 graphs here, this we'll call graph number 4. How many real zeros? It crosses the x twice, so it has 2 real. There are 3 turnarounds, therefore this is a 4th degree. If 2 of those answers are real, therefore 2 of them must be imaginary. And it's going off in the positive direction to the right, so it has a positive leading, can't even write leading, coefficient. And the last graph, graph number 5. How many real? Well, this crosses the x 3 times, so it has 3 real zeros. I'll answer the imaginaries here in a minute. The degree, 1, 2, 3, 4 turnarounds, therefore this is a 5th degree equation. If 3 answers are real, then 2 must be imaginary. And it's going off in the positive direction to the right, so it has a positive leading coefficient. All right, now you have the knowledge you need for section 6.8, so have fun with math.